Welcome to session 5 of the Data Structure and Algorithm series. In the last section, we explored asymptotic analysis, a powerful tool that allows us to simplify the comparison of the performance of different algorithms. When it comes to data structures, one of the key challenges is figuring out how to store data in memory efficiently. Our goal is to ensure that operations like searching, sorting, and updating are quick and don't waste space. In this session, we are going to focus on arrays, one of the most fundamental data structures. By applying asymptotic analysis, we'll explore how efficiently we can access, search, and modify elements in an array. We'll also see why arrays are a powerful tool for organizing data in many programming scenarios. To understand why arrays are so effective, let's consider the different forms data takes in programming, like integers, floats, or characters. In traditional approaches, you might use separate variables for each piece of data. Instead of managing many individual variables, an array lets us use a single variable to store and manage a large amount of data of the same type. This simplifies data management, making it easier to perform operations like accessing, updating, or iterating through the data. For instance, a list of student names or daily temperatures can be efficiently managed using an array, with all elements stored in contiguous memory. By consolidating data into a single array, we streamline data management and enhance efficiency in programming. This is where arrays come into play. By storing values in a contiguous block of memory, arrays allow us to efficiently manage and access large datasets. This efficient access and management make arrays an essential tool in programming. Whether it's for sorting lists, managing large datasets, or other programming tasks, arrays are a key player in organizing and handling data. In programming, arrays are used to manage and organize data efficiently across various dimensions. 1D arrays are commonly used to store simple lists, such as daily temperatures or a playlist of songs in a 1D array. Each index represents a single data point. For example, the temperature on day 3 is accessed using index 2, while the third song in the playlist is accessed using index 2 as well. This straightforward indexing allows for easy retrieval and management of data in a simple, linear structure. Overall, 1D arrays provide a clear and efficient way to handle lists of data in programming. 2D arrays are useful for more complex data structures. In image processing, for example, each cell in a 2D array represents a pixel's intensity in a grayscale image. Each cell's value ranges from 0, representing black, to 255, representing white, with various shades of gray in between. This allows us to efficiently perform operations like filtering, edge detection, and thresholding on the image. 2D arrays provide a powerful way to handle and process complex visual data in various applications. 3D arrays extend this concept to even more complex structures. In medical imaging, for instance, each element in a 3D array represents a voxel in 3D space. These voxels provide detailed 3D representations of structures within the body, allowing for comprehensive analysis. In 3D game environments, 3D arrays help manage spatial data like terrain and objects to create immersive experiences. 3D arrays enable detailed management and manipulation of complex data in various fields, enhancing both medical imaging and interactive simulations. This is nice. But what if our data is even more complex, requiring us to consider multiple layers or dimensions? This is where higher dimensional arrays come into play, providing an even more powerful tool to structure and organize information. As we move into higher dimensional arrays, such as 4D and beyond, we open up new possibilities for organizing and analyzing data. These multi-layered structures are invaluable in fields like physics simulations, where multiple factors need to be tracked simultaneously. In this session, we have journeyed the basics of arrays. Exploring them can help us manage and analyze increasingly intricate data. But our journey doesn't end here. In the next video, we'll explore arrays in more depth by looking at operations like insertion, deletion, searching. We'll also introduce arrays as abstract data types, so stay tuned, stay curious and keep exploring. Happy coding!